Welcome back to Statistics. I'm Dr. Jeff Groh. Today, we're going to first begin by looking at what we call a frequency distribution. A frequency distribution is a table. It's going to have two columns. It's going to have labels. And it's going to have number of data values. Those are called your frequencies. So it has two columns with category labels. In the first column, and the number of data values called frequencies. In the second column. So let's give an example. Suppose we divide a group of people into age groups, and we'll have our frequencies. In this particular group of individuals that we're referring to, let's suppose there's the age group from 17 to 25. And we're going to suppose that this particular group has 15 individuals that lie in this age group. The next group will go from 26 to 32. We'll suppose that we have 3 individuals in this group. And then from 33 to 40, let's suppose we have 1 individual in this latter age group. So here we have the labels for each group, and then we have the number of individuals within each of these age categories. Notice that over here, these categories are defined to have a range of values. We have a lower class limit and an upper class limit. L sub I, so this is L sub 1, L sub 2, L sub 3. These are the lower class limits. U sub I are the upper class limits. So 25, 32, and 40 are the upper class limits. We'll define the class width to be L sub I plus 1 minus L sub I. So in this case, the class width here will be 26 minus 17, so 9. After all, if you're looking for individuals from 17, 18, 19, 20, 21, 22, 23, 24, 25, that's 9 years. That's a 9-year spread. 26 minus 17 is how you get that difference. You subtract these adjacent lower class limits to find the class width. Technically, we'll define the class boundaries between these classes to be kind of the average of 25 and 26. So we're going to have the upper class limit of one category averaged with the lower class limit of the next category. There's one more concept associated with this, and that's the class midpoints. On some problems, it's better to use some kind of estimate for the middle of these. For these, we'll just average the right and left, the upper and lower class limits to find the class midpoints. When setting up a frequency distribution, you can maybe determine the class widths by taking the maximum data value minus the the minimum data value, the range of the data values. The range is max minus min, and divide by the number of desired categories. So if we wanted to divide into 3 categories, suppose we have 40 as an upper limit and 17 as the lower. 40 minus 17 is 23. Divide by 3, and you get approximately, well, a little bit bigger than our class widths. You can see that 33 minus 26 is about what? About 7. So about 7 on this one. It's a little bit bigger on this one just because of the way we randomly decided to set this one up. But typically you would want your class widths to be approximately the max data value minus the minimum divided by the number of categories. And you get to decide how many categories you want. So that will give you the approximate class width. You can round from there and use other adjustments as necessary. For a relative frequency distribution, you take the frequency in each category and divide by the total number of data values times 100%. So you're getting the proportion of data values times 100%, the percentage of data values within each category. In the last example, we had age and then number. This was 17 to 25, 26 to 32, 33 to 40, 15, 3, and 1. We wouldn't use 15, 3, and 1. Notice the total number of data values is 19. That's your n. We'll take 15 divided by 19 times 100%. On my calculator, that's about 79%. You'll give 79% in the relative frequency distribution. 3 divided by 19 times 100% gives about 16%. That's about 95% so far. And then about 5%. These are only approximate values. So in the relative frequency distribution, we would give these percentages instead of the actual number of data values, 15, 3, and 1. For a cumulative frequency distribution, we want to know, say, age and the cumulative frequencies. We want to know everyone less than 25 to begin with. That was 15. On the next category, it's everyone less than 32. We had 3 more for a total of 18 less than 32, the 3 and the 15. And for everyone less than 42, that would be 19. Note, if data is normally distributed, then if you were to graph the distribution of the data points, they would typically go from low to high and then low again. A lot of data piled up in the middle, low on both endpoints, and approximately symmetric. For common distribution shapes, we have the normal, uniform, skewed, right, kind of heaped up on the left versus skewed left. You may also have situations where you have a couple bumps. This is bimodal. What is a histogram? It is a graph consisting of bars, so it's a type of bar chart. But it's a bar chart having certain specific characteristics. All the bars are of equal width, and you can't have gaps between the bars. They have to be adjacent unless there is a gap in the data, in which case it's okay to have a bar of height 0. The horizontal scale represents the data values, and the vertical scale represents frequencies or relative frequencies. So as an example, we might have something like this: 16.5, 25.5, 32.5, and 40.5. We have these different heights. What do we have? 15 here, 3 here, and 1 here. And the original frequency distribution that we gave earlier, we can convert that into a histogram in this form. For a scatter plot, you have to have bivariate data. So you have to have an X and a Y. Two different pieces of data plotted together. An example might be shoe size versus height associated with an individual. And you might get a scatter plot that looks something like this, where you have the shoe size and the height plotted against each other. They won't be a perfect straight line, but generally, the taller a person is, the longer their feet are going to be. Not a perfect plot, not a perfect line plot. Surely, there may be people who are very tall with very short feet, and people who are very short with very big feet. And so you might end up with a scatter plot that looks something like this. Another example might be penny year versus penny weight. It turns out there was a break at about 1982, where before then pennies generally weighed about 3.1 grams, and so you had penny weights that looked like this, and suddenly they jumped down to a lower penny weight because they started making them out of zinc with a thin veneer of copper over the top. And so then they dropped to about 2.5 grams. A little different pennies might weigh slightly different amounts, and so you might have little variations. Your scatter plot might look something like this. There are graphs called time series graphs. Time series graphs only work for ratio data, but let's suppose you have a sequence of times, you might end up with data that does something like this. This might be a representation for the Dow Jones Industrial Average. You might have the ups and downs, hopefully generally trending up, but you never know. And so it definitely doesn't just go in a straight path. It has ups and downs as people buy and sell the stocks on the Dow Jones Industrial Average. There's the famous dot plot. Suppose I have a whole bunch of different data values. Uh, 33, 34, 33, 37, 37, 38, 40, 41, 41, 43. I might have three different categories here. My 20s, 30s, and 40s. How many of these do I get? 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4. 1, 2, 3, 4. And that gives a sense for the distribution of the data as well. The data needs to be discrete for this kind of plot to work out. And essentially what we're giving here are the frequencies 3, 5, 4 for these different kind of discrete data in these categories. The dot plot is very similar to a stem plot. As an example of a stem plot, suppose I have data 87, 92, 93, 98, 101, 105, 95, 115, and 82. I'm going to give my 80s, 90s, 100s, and 110s. 80s. There's an 87. There is an 82. Aha. My 90s, I have a 92, a 93, a 98, and a 95. So I have all my 90s in there. My 100 between 100 and 109, that's going to be 101, 105, and then I have 115 down here. So again, you can get a sense for the distribution of the data piling up a little bit more in the 90s than in the 80s and the 100s, and one data point out here bigger than 110. Bar graphs are a little more general than for histograms. You don't have to have these things touching each other. You just represent the frequencies in this fashion. Here you give frequencies for categorical or even qualitative data. So we might be looking at eye colors. And eye colors aren't necessarily numeric. We have what? Blue, green, brown, dark brown, and so on. And we can just put the number of, say, blue eye individuals in a group here, green, brown, dark brown, etc. So we can classify this qualitative data and then put their frequencies into a bar chart like this. For a Pareto chart, it's like a bar chart, but now you put the bars in decreasing order. With bars in decreasing order for the Pareto chart. You only use a pie chart if you have ratio data that adds up to 100%. And there you put in your, say, frequencies. In this case, let's say this is about 33%, 34%, and 33%. Has to add up to 100%. A common recommendation is that since pie charts are kind of overused, that you don't use them. Sometimes you can represent the data in a frequency distribution using a frequency polygon. And so the data might do something like this. Goes up and then down. Or who knows, it might go back up again, who knows, depending upon the kind of data that you collect. These can be either frequencies, the actual number of data elements in the category, or the relative frequencies, the percentages within each category. And ogive is similar to these frequency polygons, but we use cumulative frequencies. And since they're cumulative frequencies, it has to add up all the frequencies from before. And so you might end up with something that looks like this. It must be monotone increasing. I want to give you a sense of graphs that deceive. Suppose I'm using a bar chart, maybe even a histogram, I don't know. And suppose these numbers over here are like, I don't know, 492, 493, 492 and a half. These are really close numbers. And it looks like the variations are much bigger than half a unit here and half a unit there. And the problem is, I may be starting at 490 on the scale here. If you start the scale off someplace other than 0, it might give the sense that there are big differences when in fact those differences are not that significant. In fact, the differences might be only due to random chance in the selection of the data. So this gives a sense that there's a big difference when in fact the differences may not be statistically meaningful at all. Another thing that people do is they use volume to represent linear measures. So for example, it looks kind of cool sometimes to use these charts that have these three-dimensional kind of bars. But if you're using those three-dimensional bars to represent something that has a linear measure, then that's probably not a good way to go. If you're using it to measure a volume, like the volume of, say, water that goes over a dam in a particular year, or the volume of walnuts that are produced on a particular orchard in various years, yeah, volumes against volumes, that's fine. But volumes against linear measures, that's not fine. There's a section in your book about scatter plots, regression, and correlation, but the definitions at this point are dreadful, so I'm going to defer any discussion of that until we get to Chapter 6. I thought I'd show you how to produce some of these charts using a spreadsheet. Often students will have access to some form of a spreadsheet, like Excel. If you don't have Excel, you can use the alternative that I'm using here, which is OpenOffice. Let's get started. Let's have age and frequencies like we had in our initial example. Let's have 17 to 25, 26 to 33, and 34 to 40. Let's see, we had 15, 3, and 1. We can easily produce a chart by inserting a chart. It allows us to choose a large variety of different kinds of charts. As you can see, a pie chart is probably not recommended here. It has column charts, which are our bar charts. If I want to make this into a histogram, I have to make the gap between the bars equal to 0 in width. So I'm going to format the data series by doing a right click, and I'm going to adjust the spacing to be 0. And now I have a histogram. Let's see, on a new sheet, we might have a collection of marbles, let's say, green, blue, cat's eyes. Let's suppose we have 10, 8, and 3. The total number of marbles then is, let's see, 18 plus 3, that's 21. To get the relative frequencies, or the percentages, we'll take the number to the left, divide by 21, and multiply by 100. These formulas always must begin with an equals. If you leave the equals sign off, it won't perform the calculation. Calculation on all of these, I can just drag that formula down. Notice that the sum of these should be 100%. So now, if we want to, we can insert some kind of a chart. We can even insert a pie chart this time, which might be appropriate since they add up to 100%. Though, again, we've recommended that you not use pie charts. This is actually not too bad of a representation of the numbers within each category. Alternatively, we could have plotted this with these relative frequencies. Again, changing the format so the gap between these is 0, turns it into a histogram. We don't have to stick with blue. We can change the color of the area to whatever we'd like. You like purple, go with that. Change this to red. You can even change it so that it has boundaries or bars, edges of different colors as well. There's a lot you can do playing with this, and I'm sure you'll figure out more of the functions than I even know after playing with this for a short period of time. If we wanted to form some kind of a Pareto chart, we would need cumulative frequencies. I'm going to just choose this to be over here. To get the cumulative frequency, I'll take the previous frequency and add it to the new frequency, so that in the end we get 100%. We can graph that with these two columns. I'm pressing the Control button when I select the second column. I'll choose kind of a line here. We might want to include the dots for the points. This would give me the Pareto type of chart with the cumulative frequencies up to 100% here at the end. It's kind of bad form to have so many extra digits. It's better to have fewer digits than this. Not all of these digits are significant if we only have some of these values only having one digit. So we can format the cells in this column to have a certain number of decimal places. We can format these to have no decimal places. And same thing with these, cumulative if we wish. Format the cells, change it so that we have no decimal places. And it's probably better to give the data in this form when we choose to create our charts. And we were doing a Pareto chart last. There.